Hello, Sauce here. This is a pre-calculus lesson on infinite geometric series. Let's take a look what I've written on my paper so far. What can be said about this? I've got 1/3 plus 1/9 plus 1/27 and the ellipsis symbol, ... Immediately I can see that I have a series of fractions. It's a series because I'm adding together terms, and the fractions are the terms of a sequence that goes on and on and on. I can only see the first three terms. So what can be said about what I've written here? It's a series, a sum of a sequence. Is there a rule for generating the terms of the sequence? I'd need to investigate. How does 1/3 become 1/9? One way to do it is multiply by 1/3. And that rule holds because 1/9 multiplied by 1/3 makes 1/27. Because the rule for generating the values of the terms requires multiplication, and I can say this is a geometric series. And the rule, the constant ratio that I multiply by, is 1/3. What else can be said? Well, a series is a sum. How many things am I adding together? Not just the three that I see, but this ellipsis symbol means that this series goes on infinitely. So if I'm going to add together or find the sum of the series, I'll be adding an infinite number of fractions. All those fractions are positive, so it's natural to think that if I'm adding together an infinite number of positive numbers, then that sum is going to be infinity. But it won't be. And to see why it won't be infinity and what it might be instead, I have a demonstration using paper. Let me show you. I'm going to start this demonstration by taking a full sheet of paper and cutting it in half. So this blue piece of paper represents or is 1/2 of a full sheet of paper. I'm going to cover or begin to cover this half sheet of paper in pink. The colors are contrasted so you can see what's been covered and what's left. In a circle there, I have 1/3. That is the amount or the size of this pink piece of paper relative to a full sheet. This pink piece of paper is 1/3 of a full sheet. Now, how did I get 1/3? Well, it's covering 2/3 of the 1/2 sheet of paper. So if I multiply those fractions, it tells me how much the pink sheet is compared to a whole. I'm going to continue to do this. I'm going to follow a pattern. Of the remaining third that has left to be is left to be covered, I'm going to cover 2/3 of it. The product of these fractions tells me how much this pink piece of paper is relative to a whole. This piece is 1/9 of a full sheet. It's because it is 2/3 of the remaining third of the 1/2 piece of paper. And I'm going to repeat this process. In a circle there, this piece of paper is 1/27 of a whole. Now how we got there might be a little confusing, but the product of these fractions determines how much this piece is compared to a whole. And I can continue this pattern, always filling in 2/3 of the remaining piece, so that 1/3 is left uncovered. And I can repeat this process and keep going, and this process will never end. I can't cut small enough pieces of paper to continue much further than this, but hopefully you can see that if I'm always putting 2/3 more in there, there's always some remaining that has yet to be covered, and I can do this an infinite number of times, attempting to cover the entire half piece of paper. How does this relate to what we started with? Well, this pink piece of paper is the value of the first term of our geometric series. And every time I added a piece of paper, I was adding the next term. 1/27 is this piece of paper, represents the next term in the series. And I can keep on going infinitely. So what is the sum of this series? The sum of this series is represented by the sum of all the pink pieces of paper. And you should be able to see that if I can continue this process indefinitely, I won't have ever any more pink paper than the original blue half sheet. But if I do this infinitely, then I will eventually fill in the entire original blue half sheet. So the sum of this series is 1/2. Now how can we do that mathematically? We have a formula to find the sum of a geometric series. I need to find the value of the initial term. We can symbolize that by G sub 0, G for geometric, and 0 is the number or index of the initial term of a sequence or series. And I divide that by 1 minus r, where r is our constant ratio that we multiply by to generate the sequence. R, if it's going to have a sum, has to be in between -1 and 1. It's got to be a fraction. It can be negative or positive, but it has to be a fraction. So if I have a geometric series and the growth factor, or the constant ratio, is between -1 and 1, this formula here will find the sum of that series. Let's apply this formula to the series that we're working with here. The value of the initial term is 1/3. I'm going to divide by 1 minus, our constant ratio is 1/3. I'm going to simplify this. I have 1/3 divided by 1 minus 1/3, or 1/3 divided by 2/3. And of course, I recommend that when you have division or fractions inside of division, that we use the division symbol, turn it into fraction division, because we can easily turn fraction division into fraction multiplication by multiplying by the reciprocal. And then in this fraction multiplication, I've got a common factor that I can cancel out, which leaves 1 in the numerator and 2 in the denominator. The sum of this infinite geometric series, the sum of an infinite number of positive numbers, is 1/2. Just like the sum of all of the pink pieces of paper becomes the 1/2 sheet of paper.